All right, let's try to do this problem here. So let's talk about the two pictures first. This picture is a sideways picture of this entire road. So this is much more of a close-up than this. This is the top view of the road. Okay. So the first question involves the angle of this road right here, such that the car driving at 15 meters per second requires no friction to stay on the road like this. Okay, so let's try to draw a little free body diagram of that car. Okay, so you're going to have the road that forms a angle theta like this with the horizontal, and the car is going to have a center of gravity right here. And so the car is going to have a mass, therefore it's going to have a force Fg going down like this. The road is going to react with the car, so you're going to have a normal force right here. And here we are told specifically that there is an angle for which no friction is required for the car to keep from slipping on the road. Okay. Now, here's what we need to understand. If there was not a turn of radius r like this, then let's say if it were just at an angle like that and the car were going to be going straight, then those two vectors right here would create a net force, right, which is the sum of the two vectors. That will be like this one in red. That will be the net force, right? And if the car were to go straight, then the problem is that it will be sliding down the ramp, right? But here we know that there is no friction, which means that the car will be sliding down the ramp. And so it's not good. So why is it that the car is not sliding down the ramp? Well, it's because it's going in a turn, okay? And in a turn, you are going to have an acceleration, and the acceleration is going to be toward the center. So I'm going to draw a vector right here. I'm going to call it the vector AC, which is the centripetal acceleration, and it's toward the center of the circle. And if you need to remember, the magnitude of AC is equal to V over R square. Is that correct? I never remember. Is it V over R square or is it V square over R? Which one of those two is it? Well, I have a little technique that I want to show you at this point too. If, like me, you have trouble sometimes with the correct formula, you can remember it. AC is an acceleration, right? So let's do a little bit of dimensional analysis here. That means it's going to be meters per second squared like that, right? Now let's pretend it's the first formula that is the correct one. So V, the velocity, will be in meters per second divided by the radius square, which is meters square. Okay? Is that correct, or is this correct right here? Meters per second square equal, and then I'm checking the second one, the V square over R, which would be meters square per second square over meters. Which one of those two works? Okay. Now that's a division, so if you just want to look at the dimensions, you can say it's meters per second divided by meter square, right? So it's going to be meters per second times 1 over meter square So this top unit will be essentially 1/2 meter. That's a little strange. This one right here will be meters square per second square times 1/meters. And so this, as we can see, is going to be meters per second square. So which one of those two formulas is correct? Is it V over R square or is it V square over R? So obviously it's going to be V square over R, right? Okay. Then we're in agreement. So it's V square over R. So now that I've verified all of this, I don't need it anymore. The answer is going to be AC equal V square over R. Okay. But it's a vector. So if I want to write it as a vector, if I want to write the components of that vector, I need to define a x direction and a y direction. So for this here, I'm going to choose to have my x direction to be horizontal and my y direction to be vertical. Therefore, my vector AC, is going to be V square over R and 0. Okay, so let's write the other vectors. So we're going to have the vector FG right here. And in the x direction, FG is 0. In the y direction, it's going to be negative mg. Right? It's straight up and down. So it's in the direction of the y-axis. The y-axis, we define it as being positive going up. So going down, it's negative. And the vector n. So the vector n, we have the angle theta. That's going to be right here. Okay? The angle of the ramp can also be represented like I did right here, like that. Which means that in the x direction, we are going to have n times cosine theta. And in the y direction, we're going to have, no, my apologies here, it's not going to be a sine in the x direction, because when I project this right here, that's going to be the sine of the angle theta. That's going to be n sine theta, and it's going to be n cosine theta right here. Okay? Now, what does Newton's second law say? Well, it says that the sum of the forces, which is also the net force, is equal to the mass times the acceleration. Okay? And so we're going to project that in both directions. So in the x direction, the force, the sum of the forces in x direction is going to be. So you're going to have the normal force, n sine theta, plus the force, the weight, the mass times gravity, Fg in x direction is 0. And that's going to be equal to V square over R. Okay, beautiful. The sum of the forces in the y direction, it's going to be equal to in the y direction. So we have n cosine theta minus mg, and that is going to be equal to the mass times the acceleration. The acceleration in the y direction is 0. Okay. Oops. Did I forget the mass on top for the top equation? Yes, it appears so. Okay. So I'm going to move this right here so I can write mass times acceleration, not just the acceleration. Okay. So let's try to remember what we're looking for here. We are looking for the angle theta at which we don't require a force of friction to stay on the ramp. Okay, so we are looking for theta. So if I call the equation right here equation number 1, and if I call this equation number 2, then equation number 2 will become n cosine theta equal mg. And then I'm going to essentially do equation number 1 divided by equation number 2. This is going to give me n sine theta divided by n cosine theta. So it's going to be essentially the n and the n cancel. So it's going to give us tangent theta equal mv square over r over mg. So it's going to be v square over rg. Therefore, theta is going to be arctangent of v square over rg. All right, so now do we know all those values? Well, from what is given in the problem, we know that the velocity, the target velocity for this ramp is 15 meters per second. We know the radius of the turn like this is 50 meters. And we are going to assume that we are doing that on Earth. So that's going to give us right here 9.8 meters per second square. Okay, so calculator time. So 15 square divided by 50 times 9.8. All of this is going to be 0.459. And then I'm going to set my calculator in degrees. And I'm going to take arctangent of that number. That gives me an angle equal to 24.66 degrees. Okay, so we are going to have a banking angle for this road equal to 24.66 degrees. Okay, very good. All right, let's look at part B now. What is part B about? What minimum coefficient of friction mu s is necessary so that the car at rest on this section will not slip sideways? Okay. So the car will be at rest. Okay. That means the acceleration will be equal to 0 in that case. Okay. So the car is at rest. That means that the acceleration vector is going to be the null vector like that. All right. So let's draw the free body diagram again for this vehicle. So you're going to have the inclination of the road like this. This is still going to be our angle theta. We are still going to have our vector fg right here. We are still going to have a vector that is normal to the road like this. Remember, normal means perpendicular. And like I told you earlier, the net force has a tendency to make the car slide down right here. And that means that the friction is going to prevent that movement. So we're going to have a force of friction going opposite this. So I'm going to call it FF like this and write it like that. Okay. Now, in order to determine the coefficient of friction, it would be a fantastic idea to know the definition of that coefficient of friction. Okay, and it's it doesn't have any quantity. It's a ratio of magnitude of forces. Okay, so the coefficient of friction, it's the force of friction divided by the normal force. Okay, so how are we going to handle all of this? Well, we need to express those vectors. We need to talk about the coordinates of those vectors. And so what I'm proposing to do is that we set up a system of coordinates, because we don't need to work with the centripetal acceleration right here that is toward the center of the rotation. It's not moving. Remember, we are at rest right here. Then what we're going to do is, in order to simplify the math a little bit, I'm going to define my x-axis as being like this, in this direction, and my y-axis to be in this direction. In other words, the friction is in the direction of x and the normal force in the direction of y, and then we just need to deal with gravity. Okay, so let's do that. So based on this, the force of gravity is going to be in the x direction, it's going to be positive, so it's going to be mg, and theta is there, so it's going to be sin theta. And in the y direction, it's going to be negative mg cosine theta. Okay. The normal vector in the x direction will be 0, in the y direction will be this. And the force of friction would be negative ff and 0 like that. Okay. So we're going to use Newton's second law again, but we're going to use the sum of the forces equal to 0. It's a static problem, things are not moving, so plus the acceleration is 0, so we have this, which means that the sum of the forces in the x direction is 0. Therefore, we're going to have mg sine theta equal the force of friction, and the sum of the forces in the y direction is equal to 0. Therefore, negative mg cosine theta is equal to n. Okay. Now, if you look at the formula for the coefficient of friction, we see that it's the ratio of those two. So if I call this equation 3 and if I call this equation number 4, dividing 3 by 4 will yield this answer, mg sin theta over negative mg cosine theta. The mg is cancelled, so you're going to be getting sin theta divided by cosine theta, so tangent theta. Okay. And this is going to be a positive. I made a small algebraic mistake. And it's going to be equal to the force of friction divided by the normal force, which by definition is the static coefficient of friction. Okay? So the static coefficient of friction, therefore, it's going to be what we calculated earlier. It's going to be the 0.45918 number that was just the v square over rg. Okay, so I know that the problem didn't ask for it, but essentially, if you want to express the static coefficient of friction in relation to the velocity at which there is no friction, the radius, and gravity, well, it's just going to be equal to v squared over rg. Okay. I don't know if it's interesting to anybody to see that, but here you go. Okay. Oops. All right. Part C. What are we asked to do in part C? For this coefficient of friction found in part B, what is the maximum speed a car can drive on this section without slipping sideways? Okay, so we are looking for the maximum speed we can drive on this road. All right, so let's draw another free body diagram. Okay, so we have the road, we have this. This is our angle theta, so it's our 24.66 degree angle. We have our car. Again, this is going to be FG. We are going to have our normal force. And the car is moving now. It's moving pretty fast, actually, or it's going to be moving pretty fast. And so the car has a tendency to want to go straight and to go essentially to leave the curve of the road. So the car is going to, how do I put it nicely? The car is going to want to go in that direction, up the ramp. This is what the car wants to do right here. It wants to go there. And that's why we have tires with high grip. Because we don't want to let the car do this. So, what does that tell us? Well, that tells us that the force of friction, it's going to be in this direction right here. The force of friction is going to be this. Okay? And the acceleration, it's still going to be like this toward the center. Okay? So, we need to use Newton's second law. So I'm going to define another x-axis and y-axis. Okay? And I'm going to make my x-axis like this, my y-axis like this, and I'm going to express each one of those vectors with all of that. Okay, so for Fg, you're going to have a 0 in the x direction and negative mg right here. Very good. The normal vector, this one is the difficult one, but it's okay because we did it already. It's going to be n sine theta in the x direction and n cosine theta in the y direction. Then we have the force of friction. Okay, and the force of friction in the x direction would be positive, so it's going to be ff, and it's going to be in the x direction, so cosine of the angle theta. And in the y direction, you see it's going down in relation to the y-axis, so it's going to be negative ff sine theta. Okay, so I'm writing sine theta, but we know the angle theta. Okay, we know it's 24.66 degrees. Okay, the thing that we don't know is the velocity. In other words, we don't know the centripetal acceleration. Right? So we're going to have the sum of the forces in the x direction. That's going to be equal to 0. So in the x direction, we're going to have n sine theta plus force of friction cosine theta, and it's going to be equal to mv squared over r. Okay, remember the centripetal acceleration, it's the same as what we have right here. So v squared over r in the x direction. And in the y direction, you're going to have negative mg plus n cosine theta minus the force of friction times sine theta. All of this is equal to 0. Okay? So the issue right here is that we cannot do a nice, neat little ratio like we did before, because it won't simplify just like we did before. So we have a lot of methods available to us, but if I've called this equation number 5 and equation number 6, what I'm going to do here is I'm just going to isolate n in 5, then I'm going to isolate n in 6, then I'm going to make them equal to each other and see if I can isolate v again. Let's keep in mind what we are trying to do. We are trying to find v right here. Okay. So let me change color so that it's easier to see. So you're going to have n is equal to, so you're going to have mv squared over r minus the force of friction right here times cosine theta. Okay, that's n sine theta. So we need to divide all of this by sine theta. So I'm just going to put it right here for now. So that's going to give me mv squared over r sine theta minus the force of friction cosine theta over sine theta. Okay. Let's see what the second equation gives us. All right. So in the second equation, we are going to have n equal. So when I put the other two on the other side, that's going to give me the force of friction times sine theta plus mg. And I'm going to have to divide all of this by cosine theta. So I'm going to have cosine theta here and cosine theta here. All right. So those two are equal. So you're going to have mv squared over r sine theta minus ff cosine theta over sine theta equal the force of friction like this times sine theta plus mg over cosine theta. Okay. And remember one thing, we are looking for v squared. Right? Okay. So let's try to simplify a few things right here. Okay. Now, this here is FF, the force of friction, and we know that this is equal to, let's look back up here, is equal to mu times n, right? So we know that this is equal to mu times n, mu times n. Oh, maybe we should have taken the time to do that before. Maybe we should have replaced that by mu times n right here and right here before isolating n. That would have saved us some time. Okay, no big deal. We need to stay flexible when we do anything. So I'm going to go back to equation 5 and 6 up there, and I'm going to get rid of the work that I've done right here. This is not bad, but I can do better than this. Okay, so in equation 5, we're going to have n sine theta plus mu n cosine theta equal mv squared over r. That means here we're going to have n times mu cosine theta plus sine theta equal mv squared over r. Okay, and in equation number 6, you're going to have negative mg plus n cosine theta minus mu n sine theta equals 0, which is going to be n times cosine theta minus mu sine theta equal mg. All right, that looks a little neater to me. I prefer this. So let's make equation 5 equal to equation 6. And so that's going to give us mv squared over r times mu cosine theta plus sine theta is equal to mg over cosine theta minus mu sine theta. Okay. Now, as I expected, the mass of the vehicle does not matter. That means I can cancel those two m's. Which means that I can rewrite v squared, remember that's what we're looking for, as rg times mu cosine theta plus sine theta over cosine theta minus mu sine theta. Therefore, v is going to be the square root of all of this. So it's going to be rg And here we're going to have mu cosine theta plus sine theta over cosine theta minus mu sine theta. All right, we're almost done. Now we're going to replace by the variables by their value. So the radius of the turn is 50 meters. G is 9.8 meters per second square. Mu, the coefficient of friction, we got it in B, it's 0.45918. 0.45918. And the angle theta is the banking of the road, and we add 24.66 degrees. Okay, so we're going to enter all those values in our calculator, and it's going to be the maximum speed that we can safely use without skidding, without anything bad happening to us. All right, so calculator time. So 0.45918 times cosine 24.66 plus sine of 24.66, here we go, divided by cosine 24.66 minus 0.45918 times sine of 24.66. This big ratio, I get 16.36. I'm going to multiply it by 50. I'm going to multiply it by 9.8, and I'm going to take the square root of this thing. And I must have made a mistake because 89.56 meters per second is way too fast. So let me do it again on my calculator. Mu 0.45918 times cosine of 24.66, 0.417. Okay. Plus sine of 24.66, 0.83, divided by cosine 24.66 minus 0.45918 times sine 24.66, 1.16. Okay, that is different. I don't know what I did wrong earlier. And that gives me a speed of 23.87 meters, 23.877 meters per second. Okay, so this is how fast the car can go safely without skidding, without getting off the roads. So there you go. Okay. Now, some of you might be interested to know approximately what this is in miles per hour. This is about 53.4 miles per hour if you want to know about this. All right. If you have questions, let me know.